Welcome to the electronicsHobbyblog.com. I'm your host, Dominic Soldano, and today we're talking rotary encoders. Rotary encoders are quite useful devices. They can be used in place of potentiometers. The fact that they rotate almost infinitely means you can use them to select from a large number of menu choices, and the push button allows you to click when you get to the choice you want. They're especially useful when they're combined with a microcontroller. And today, we're going to learn how to hook them up, how to debounce them, and how to use them with your favorite microcontroller. So if you want to know more, stick around. Here's a few different types of rotary encoders. Here are some without and some with breakout boards. In fact, one of these, the shaft of the rotary encoder lights up. And on another one, it's got a bar graph ring around the rotary encoder, and the bar graph lights up progressively as you turn the rotary encoder. There are three basic types of rotary encoder. Optical, which uses a laser and an etched wheel that breaks the laser beam. Magnetic, that uses a magnetic wheel and Hall switches to create pulses as the rotary encoder is turned. And the most common type, most often used by hobbyists with microcontrollers, is the mechanical rotary encoder. And that's what we're going to be using today. A mechanical rotary encoder uses an etched wheel inside the encoder and a set of wipers that wipe along the wheel. Gaps in the copper create breaks and end up creating pulses within the contacts. The contacts are slightly offset so that as the wheel rotates and passes by each contact, it creates a phase shift in the pulse train that's coming out of the mechanical encoder. The most common type of mechanical rotary encoders, and the ones we're going to use today, are quadrature encoders. And they're called quadrature encoders because they actually exhibit four separate states. And you'll see those in the state table, and we'll go through each of them here. Notice that when you turn the encoder in the clockwise direction, the pulse train for B is phase shifted earlier than the pulse train for A. And that causes a very distinct set of values between A and B. Likewise, when you turn the encoder counterclockwise, then A leads B. And again, it creates a series of pulses, and if we look at each phase of those pulses, and there are four phases as you can see in the state table, we can determine which direction the rotary encoder is turning. Each time we turn the rotary encoder one detent, we end up going through four quadratures. Each quadrature has a different state of A and B. So we're going to start with both A and B low, or 0. When we turn the rotary encoder a little bit, A goes high and B stays low. When we turn it a little bit more, now both A and B are high. A little more, B goes high and A goes low. And finally, we get back to the beginning with A and B both low. The encoder goes through those four quadratures for every detent. That's going to be important when we write the software to determine how many clicks the rotary encoder's been turned. So let's look at how we connect a rotary encoder. Simple rotary encoders that incorporate a push-button switch actually have 5 connections. 2 connections for the switch and 3 connections for the encoder. The encoder normally has an A and B output and a common. We need to pull the A and B outputs and one side of the switch high. And we do that with 10K pull-up resistors. The common and the other side of the switch are normally tied to ground. This way, as we rotate the encoder, we'll get a series of 1s and 0s where 1 is equal to V+. So if we're going to be using this with a 5-volt microcontroller, we want to tie those pull-up resistors to plus 5 volts. And if we're going to use it with a 3.3 volt microcontroller, as I'm going to do today, we want to tie them to 3.3 volts. When you're dealing with a rotary encoder on a breakout board, things can be a little bit different. For instance, the rotary encoder that I have, I got 5 of them off of Amazon for about $10 delivered. They come on a breakout board, and they already include the pull-up resistors. In fact, the pins on the ones I have, and they're very common, so you'll probably encounter them if you buy some, the pins on the ones I have are labeled clock, data, plus V, ground, and SW. A big problem with rotary encoders, and in fact with any type of mechanical switch, is bounce. Bounce is what occurs when the contacts first close because they don't lock together. They do in fact bounce. Right? That's a mechanical function of one piece of metal hitting another. And so here we've got the rotary encoder wired up with just the pull-up resistors, nothing else. And I want to show you what happens when we turn the rotary encoder. So here's what we see on the oscilloscope for the A and B pins when we turn the rotary encoder. Look at all that noise. A microcontroller might interpret each of those little bits of noise as a separate pulse. And so what you end up with in this case is a huge mess. So this is a perfect example of switch bounce and why switch bounce would be a problem. One of the most common ways of dealing with switch bounce is to use a capacitor. I've put some 0.1 microfarad capacitors across each of the data lines to ground. Since the voltage across a capacitor can't change instantaneously, it prevents all that jumping around. Let's take a look at what that looked like on the oscilloscope. And here you can see that most of the bounce is gone. There's a few little spikes, but I doubt they would have much effect. We've essentially eliminated most of the bounce. And in fact, we can probably use the circuit just like this. But there's still a chance that we'd have some problems with an errant pulse here and there caused by some switch bounce that happens to get through the capacitor. So one way we can correct that is either in software, we can put in a delay when a pulse is determined and then ignore any other pulses for a while, and that will effectively eliminate the bounce because we won't be looking for it during the delay period, right? It'll give it time for the bounce to settle out on its own. The problem I have with that is it takes away compute power. You've got to put a delay in there, and that means that your subroutines can't be doing what they need to be doing while you're in the middle of the delay. So instead, we're going to deal with it in hardware. So in addition to the capacitors, we're going to add a CMOS buffer into each of the lines. And here's where I've done that using a CD4069 CMOS buffer, which operates at the same 3.3 volts as my microcontroller. And each of the data lines goes into a non-inverting buffer. And let's see what the output looks like on the oscilloscope. Here's that circuit with the buffer IC installed. Now let's take a look at what the output looks like on the oscilloscope. And if we look at the pulse train now of the A and B lines after passing through the buffer, and I gave this a pretty rapid spin, so there should have been plenty of noise. It's as clean as a whistle. We've effectively debounced those lines, then there won't be any problems. And I did the exact same thing with the switch. So once we've got it all set up and debounced, the next step is to connect it to the microcontroller. Now you can use an Arduino, you can use the Arduino Nano, you can use a Teensy. I'm using a particle photon. That's one of my favorite microcontrollers to use in my projects for a number of reasons. It costs about the same amount as an Arduino Nano, about 20 bucks. It includes wireless built in. It's got more than 2 interrupt lines, which I think is one of the limitations of the Arduino Nano. It's got a true DAC, actually 2 true DACs. Unlike the Arduino's ADCs, the Photon has a 12-bit ADC. And there are some other reasons I use it as well. For one, it's a 120 megahertz ARM Cortex chip, so it's got a lot more power. And the wireless means I can program it over the air without having to plug it in. So if I embed it in one of my projects and I later want to update the software, I don't have to pull the chip out in order to reprogram it. So here's how I hook that up to the Photon. I use 3 separate lines, A2, A3, and A4, and each of those will have an interrupt assigned to it. And it's just a straight connection to those pins. Because I did all of the buffering at 3.3 volts, I don't have to worry about level shifting, I don't have to worry about any of that, just connect it right up. If you were using an Arduino, you'd probably use your buffer at 5 volts, and again, you can connect it right in because you've already buffered it at the 5 volts. Let's look at the software and see how we use software to interpret what the rotary encoder is doing. Let's start with variable definitions. Here we've defined two main functions to act as interrupt routines. One will respond to button presses, and the other will respond to rotation of the encoder, basically a change in the encoder's state. Last encoded will allow us to check to see if the current encoder state is different than the last encoder state, meaning it's been rotated. Encoder value is a user variable that we can use to keep track of a number based on rotation of the encoder. In other words, as we turn the encoder right, we can increment encoder value, and as we return the encoder left, we can decrement encoder value. And in fact, we will. So for instance, if we were building a volume control with volume from 0 to 255, every time we rotate the encoder to the right 1 detent, volume would go up by 1, and every time we rotate the encoder to the left by 1 detent, volume would go down by 1. The other thing we need to do is to define the pins that we've defined, and we've given them more useful names. So for instance, A2 is encoder pin 1, or the A channel. A3 is encoder pin 2, or the B channel. And A4 on our microcontroller we've defined to be the button pin, or the actual switch. We've set up a number of pins as outputs and hooked up LEDs to them so that we can see what's happening with our software and know that it's working correctly. We've taken a red LED and connected it to pin D0. Whenever we turn the encoder to the left, that LED will light up. We've taken a blue LED and hooked it up to pin A0. So whenever we turn the encoder to the right, we'll have that LED light up. And we've taken an amber LED and hooked it up to pin A5 so that whenever we press the switch button on the encoder, that LED would light up. And those have no other purpose than to show us the software is working. Next is the setup code. And in the setup code, we set our pins as inputs and outputs, and then attach the appropriate interrupts to those pins. So pin A5 is set up to issue an interrupt on a falling signal. So that falling signal would occur when we release the switch, and it calls a routine called button press. Encoder pin 1, which is A2, is set to issue an interrupt whenever the state changes, either high or low, and that will call a subroutine called encoder rotated. Pin A3, which is encoder pin 2 or our B channel, is also set to issue an interrupt on a change, and it will also call the encoder rotated routine. Next is our loop. That delay is only there so that we can see the lights. Otherwise, they would flash very rapidly. You wouldn't need that delay to respond to the encoder. The 3 lines after that, the 3 digital writes, simply turn the LEDs off. And again, those aren't required for normal rotary encoder code. Those are just here so that we can see what's going on with our software. When we press the button on the rotary encoder, it calls this routine. And in this case, all it does is turn the amber LED on. So here's where we interpret what's going on with the encoder wheel, whether it's being rotated right or left. Whenever one of the pins for the A channel or the B channel, which would be A2 and A3 on the microcontroller, change state, it kicks off an interrupt which calls this routine. And we read the state of each of those encoder pins using the digital read function. And we take those and we create a bit field with a most significant bit and a least significant bit. And then we take the last encoded value, which is the previous state of those pins, and we create a bit field or a byte field. It's 4-bit. Then we examine those 4-bit to see what the state is of those 4 bits. So for example, if they used to be 1, 1 and now they're 0, 1, then something's changed. If they used to be 0, 0 and now they're 1, 0, then something's changed. Or if they used to be 1, 0 and 1, 1 and now they're 1, 1, then something's changed. So that first if statement that's commented out looks at each quadrature in the state table, and it will issue a change if any one of those quadratures has changed. So essentially that first line will register 4 changes for each detent. So I didn't want to do that. I only want 1 change per detent, and I want to get 4 clicks out every time it clicks 1, so I want to get 1 out. And so I'm just looking at the first state, and if that state changes, that means it's gone through a full quadrature. In that case, we increment the encoder value ++, increment it by 1. So if it was 10, it's now 11. I turn the LED on to show that it was turned to the right. The second commented out if statement and the second if statement that isn't commented out determine if things have changed in the other direction. In other words, the encoder's been rotated to the left. And again, the first line that's commented out would give you 1 click per quadrature, or +1 per quadrature. So your encoder value would go up by 4 for every detent that you click it. If you use the second line, that will give you +1 or -1 in this case per detent. And then of course we turn the red LED on, and then we set last encoded equal to encoded so that we're ready to look for a change on the next round. And that last 2 lines, that just keeps you from getting less than a 0 value. Well, I hope you enjoyed that. If you did, then give me a like and smash that subscribe button. Please feel free to share, and as always, on-topic comments are appreciated. Until next time, cheers.